Hello everyone, welcome to TLE Eliminators CP-31 Sheet Solutions. Today we'll be discussing the 1600 rated problem. Keshi is throwing a party. So yeah, we can pull up the sheet. It's the 19th problem. And we can go ahead and solve the problem. Okay, so let's read the question. Keshi is throwing a party and he wants everybody in the party to be happy. He has N friends and his ith friend has I dollars. If you invite ith friend to the party, he'll be happy only if AI people at most are strictly richer than him and BI people at most are strictly poorer than him. Alright? Keshi wants to invite as many people as possible, find the maximum number of people he can invite so that every invited person is happy. Right? And then we have some values of AI, BI. So let's just take this example. Right, n goes up to 2 times 10 power 5, so we can obviously write expected time complexity is obviously big O of n log n. Okay, and let's take an example and try to understand what's going on. Okay, example. So for example, here we have 1 2 and 2 1 1 1. Okay, and basically since the ith friend has I dollars, that means that the first guy is the poorest, right, and the last guy is the richest. So when we are going down the list, we are going from poorer to richer. So basically what is happening is, for example, if we consider this person, this individual can only be invited to the party if, so this is the number of people who can be poorer than him. So it's allowed up to at most one element before, and also at most two elements afterwards. Okay, at most two elements afterwards. Fine. So let's assume that we picked this, right? We picked this. Then the next choice is we can either pick this one or we can pick this one, and both work, right? Both will work because this is a constraint of people before, so at most two before and at most one after. Similarly, this is at most one before and at most one after, right? But all three cannot be taken. Because see, here's a condition of at most one before, and if we take all three, then two will be before, right? So we cannot take all three. Okay, and now we just need to find the maximum n for which we want to find the maximum people which we can invite to this party. Okay, and here obviously, so we're going to try a bunch of ideas. Like obviously for any question you have to try a bunch of examples. You'll quickly observe that greedy strategies seem pretty hard, right? Greedy strategies don't seem that intuitive, although one observation you can make, right? So one observation we can make is that if we can invite n people, all right, invite n people, or there exists a way to invite n people, then there exists a way to invite n minus 1 people also, right? Then we can invite m less than n people. Fine. As well, there exists some way to do this. Fine. And why is this observation even important? Because see, first of all, it's very obvious, because if we can invite two people, right, and we remove one of them, then that's not going to change anything. It's just going to reduce the number of conditions we have. Okay, it's just going to reduce the number of conditions we have, right? Because each condition is at most x, at most y. So those are the conditions which we have. If we remove an element, the conditions will still be met, right? So that's why if we can invite n people, then m less than n people are also possible, right? So why is this important? Because after making this observation, your brain will get the idea, right? Like, okay, maybe we can do binary search because this is monotonic, right? This is monotonic. So that's the intuition for why we can do a binary search, right? So let's say if we can invite, the maximum number of people we can invite is n, then that means that there exists some way to invite all these numbers less than equal to n, and there exists no way to invite anyone above this value, right? Any number of people above this value, there is no way. Less than this value, there is a way, right? So what we can do is we can obviously have L equals 1, R equals n, and try and perform a binary search on this, right? And find the target value, right? So best value. Fine. Okay. So now our problem simply reduces to thinking about, given that we have exactly x people, okay, given that we want to invite exactly x people, that we want to invite exactly x people, how do we check that quickly? Okay, how do we check that quickly? And not going to lie, the observation is not very straightforward. It is simple. It's a very simple observation. So I want you to pause the video, try to think about how to do this, because obviously thinking about binary search is not that hard. But then how to figure out the predicate function, how to figure out how to check x, it is in a way very simple, but in a way very tricky as well, because it's not that intuitive to think about. So yeah, I want you to pause for a moment and think about it. Okay, so think about it. Okay, if we invite x people, then let's say these x people are x1, x2, x3, x4. Let's say it was 5, so we're inviting 5 people. Okay, or let's just say there are 5 people, x is equal to 5, so we have the people we can write as a1 b1, a2 b2, a3 b3, and a4 b4, a5 b5. This is going to be the first person in your solution if there exists an optimal solution. Okay, so what are the conditions he needs to satisfy? Okay, so this is our person 1, and person 1 is at this point, so exactly 0 people are behind him, right? So 0 people behind, and there has to be at least 4 people ahead, right? So 4 people ahead, right? So the condition which this guy needs to satisfy is that a of I must be greater than equal to 4, and b of I must be greater than equal to 0, right? Similarly, right, and what are the conditions? What are the conditions the second number must satisfy? We need that b of I should be greater than equal to 1 because it has one number before it, and a of I should be, what do you say, greater than equal to 3 because at least 3 numbers we're gonna get after this, right? And so on. We get similar conditions for the rest, right? We get like this, right? And we get these conditions, right? These kind of conditions. Now the thing is, no matter which number you pick, right, no matter which person you pick, as long as the first person satisfies this condition, right, and the second person picked satisfies this condition, and the third person picked satisfies this condition, and so on, no matter which people you specifically pick, this pattern is perfectly valid, right? This person is perfectly valid. So we can just do a greedy strategy, right? Like this rules will still be valid, and so we can just do a greedy strategy. Whoever is the first person to satisfy the conditions for the first person, we'll make him the first person, right? He'll become the first person, and then after that we look for the second person, right? And then whoever is the first person to satisfy this, we'll take him, so on and so forth. So greedy strategy: pick the first person satisfying the constraint for the ith person, right? Pick the first person who satisfies the constraints of the next person, right? Constraints for the next person, because obviously if we choose someone before, then we have more chances to choose someone later, right? So satisfy the next person. So obviously this greedy strategy kind of works, right? So that's pretty much it. The way we can simulate this is we can basically be like count of people who have come before, right? So b should be greater than count of people who have come before, right? So let's call that c, and a of I should be greater than greater than, let's say, x minus c. So x minus c means the total number of people minus the people who have come before, minus 1 for the current element, right? So x minus c minus 1. So when these two conditions are satisfied, then we can choose the ith element, we can choose the ith person, we can choose person I to be the cth person in our lineup, right? We can choose person I to be the cth person in the final, in the choice, right? And the choice. And if we can do this and we can successfully choose the first person, second person, third person, fourth person, fifth person, like basically if we can choose total x people, if total x people can be chosen, if total x people we can choose, or even greater than equal to x, as long as we can choose x people, then it's possible to create a way to invite exactly x people, right? Then we can invite exactly x people. We can invite exactly x people, right? So this is a simple big O of n way of checking whether we can invite these people. So this time complexity for the check function time complexity is simply big O of n. And if we binary search in the range L equals 1, R equals n, then the total search space is also size n. So the overall time complexity for this solution will be big O of check function times the search space log of search space, big O of n times log n. Right? So that's the overall time complexity for the solution. Extra memory used. So we'll need obviously big O of n memory to store the A of I, B of I. But if you see extra memory used, then extra memory used will be big O of n, right? So the memory complexity is obviously big O of n. But extra memory from the input, right? So the AI BI values are already in the input. The extra memory we're using is just big O of 1. Okay. So now let's have a look at the code for this problem. Right. So we defined just global n and global v so that we can use our check function easily. Okay. So now we input n, we resize the vector and we input the values. This is going to be a binary search portion. So L goes from 1, R to n, right? So while L is less than equal to R, we'll do a binary search logic. Best is going to store the final answer, right? Best is going to store the final answer. What we do is obviously we do mid is equal to L plus R by 2. We do the check on mid, right? So if it's exactly possible to make mid number of people invited to the party, and if it's possible, then obviously we maximize best with this mid. We make L equals mid plus 1, otherwise make R equals mid minus 1, right? So it's a standard safe wala binary search, right? And then in the check function itself, we need to choose total of x people, right? So we'll set c equals 1 and we'll say so the first condition was, what is that? B of I should be greater than equal to c, right? B of I should be greater than equal to c. That's what it is. V of I dot second is greater than equal to c. And the second condition is that A of I should be greater than equal to x minus c minus 1, right? So as you can see, A of I is greater than x minus c minus 1. So just check both the conditions. If they satisfy, then we can take this person. So since we're taking this person, we can just do c plus plus, right? For the next condition. If we can take at least x people, then we return true, otherwise we return false, right? That's about it. Pretty straightforward binary search solution. But yeah, a little tricky if you don't get the logic of thinking of, okay, we fix the first person, then what are the conditions? We fix the second person, what are the conditions? If you don't get this logic, it might be a bit tricky. But yeah, if you practice enough greedy and binary search problems, you'll get the idea pretty quickly, right? Alright, then that brings us to the end of this video. Do absolve it, right? And do code it out yourself just to make sure you understood it. Thank you for watching and see you next time. Bye bye.